Oh shoot, excuse me. There. Do you notice how good I am at not swearing? I'm always impressed by that. I think lesser people would swear more than I would. Okay, so what's chapter 14 going to deal with? We're getting close to the end. I know it's halfway through, right? So this is hump day. I guess this is hump day for the quarter. So over the next 3 weeks, we're going to learn about really just 2 more things. This week's going to be devoted to 3 sections from chapter 14. And this is going to do with multivariate functions. So functions of several variables. So you've got a little taster of that. You do know what it's like, but we're going to get into it in a lot more detail with a lot more features. In particular, we're going to look at how do you differentiate multivariate functions. But the first thing we're going to do is describe what they are, show you what they look like. Second section is how to find limits in continuity, just like a normal function. And then the third and final part of chapter 14 is going to be finding its derivatives, and they're called partial derivatives. Pretty interesting part of mathematics, actually. And then after that, the last two sections are going to be dealing with sequences and series. Chapter 14 is interesting because chapter 14 is where Calc 4 starts. So when you do Calc 4, you'll actually begin by getting a kind of quick summary of these 3 sections. And then off you go. And essentially, excuse me, I'm going to mute everybody because there's some kind of electronic sound coming through. So as I was saying, we're going to be looking at chapter 14, and that's where Calc 4 is. So Calc 1 had a theme, how to differentiate 2-dimensional functions and what you can do with them. Calc 2 is how do you integrate 2-dimensional functions and what can you do with them. Calc 3 had no theme. Have you noticed that? Well, there's kind of 3D theme right now, but once you do the last section, sequences and series, there isn't much of a theme, just bits and pieces. And then Calc 4 is going to be how do you differentiate and integrate multivariate functions, and what can you do with them. So Calc 4 is a bit like taking Calc 1 and 2, which only use y equals f of x, and convert them into how do you do calculus, differentiate and integrate functions like f of xy equals x cubed plus y squared, right? Multivariate functions like that. And in particular, 3-dimensional functions mostly. So that's the big picture. Let's get stuck in here. Right. Let me show you some of the ways in which a 3-dimensional function could be written. That's an example of one. That's an example of one. And they're just 2 different notations. Typically, x and y are the most common variables used, and z obviously would be the third one. But z can be replaced by this. That's a bit like saying y equals x squared and f of x equals x squared. You know, back in the old 141 days, that notation was pretty common. You can also have and when it's written this way, they're called implicit. Okay. Or to be really precise, implicit equations. And when they're written that way, that would be the equivalent of, I don't know, x squared plus y squared equals 1. Now, these all represent an infinite number of points in 3D space. Now, how is there 3D? Well, you can see it. One dimension is X, second dimension is Y, third dimension is Z. So that counts as a dimension, so do these X and Ys. These count as separate dimensions. So what you are looking at when you see an expression like that, for instance, if you write it this way, you're looking for all the points in three-dimensional space which have the relationship that if you square the X coordinate and you add the square of the Y coordinate, that will equal the Z coordinate. So you can imagine all the points in 3D space. So what do these things tend to look like? Well, all of them tend to be surfaces. In fact, you might recognize this one. What kind of surface does this particular function get you?
Sphere.
Not just the sphere, but you're right. But if you're being lawyer-esque, the surface of the sphere, right? Right? Because it is only the surface. If you say the sphere, you might also mean, which you don't, all the points inside the sphere, for instance, right? So it's only the surface. So when you do fellas that look like this, you can end up with shapes like cones, right? The surface of a cone. And you can end up, and I'm really bad at drawing this, can you imagine just a curved surface? You know, like my hands are moving up and down here, moving up higher, right? The curved surface. You could get anything, right? You can get some weird and wonderful surfaces as well. Essentially, any combination that you could possibly think of counts. So what makes it, theoretically, anyway, why is this a function? Well, if you did the good old-fashioned definition way back in, say, Calc 1 days, actually even before that in Math 141 days, isn't a function has the property for every value of x, there can only be one y value, right? Well, that essentially what a function meant, right? Well, if we extend it now to Calc 3, for every pair of coordinates, there can be only one z value. So normally we think of a function in the 3D space by thinking of choosing a point here in the xy plane, and then for that point there's a unique value of z that corresponds to it, and then you pick another guy and there's a unique value z, and you pick another guy and a unique value z, and then the surface kind of follows it. So from the perspective that we want to look at functions as the floor, the xy coordinates are essentially where the domain is, right? The usable, instead of the usable values of x, the domain now becomes the usable coordinate pairs, x and y. And for every one of those x and y's, there's just one height at any given point. So technically speaking, that doesn't count as a function, it counts as an equation. So that's why I had to change its name. Well, what I'm going to do is spend a few minutes having some fun. I'm going to use GeoBra. Hopefully you can see it. You're looking at GeoBra, GeoGebra, whatever you call it. Right. This is what z equals x squared minus y cubes look like. You see it? All the points there. Let's try something different. Suppose I put a plus y squared. Quite a big difference, isn't there? Do you see that guy? It's there are lots of names for them if you're into naming things. And this one here is called. You basically take a name and you stick oid at the end, and some of them flow off the tongue, and some are like tongue twisters. This is a parabola. See, it's a tongue twister. Paraboloboid, right? Parabola oboid, right? Paraboloboid. That's a tongue twister to me, right? But you can imagine, you know, different shapes, different surfaces get generated. You get some really cool stuff. I hope it takes this. It would be really cool if it did. Imagine you took all the points whose z coordinate was the sine of the x squared plus the y squared, right? Now, I could tell a couple of things about this function right off the bat. Won't the biggest value of z be 1 and the smallest value of z be -1? Isn't the sine of anything, no matter how weird the thing is, isn't the biggest number for the sine of anything 1, and the biggest value you get out is sine, the smallest is -1. So let's see what this guy looks like. Whoa, he did look cool. Wow. That is interesting. I honestly did not expect that kind of complexity. Wow. I have no idea what that is doing. It's doing lots of stuff, but it's kind of cool. I can't think of any practical use for a function that does that, but maybe something to do with sound. You know, can you imagine somewhere? Now, I don't know how you do it, but if you could plug that into some sound synthesizer, I may have just created one of the coolest sounds out there. I have no idea what that would sound like. It probably would sound like a cat that caught its tail in a door, which probably means it isn't that worth it, but it's kind of cool, right? Now, if you take as a simple example, z equals x plus 2y. Do you know that's just a rearrangement of x plus 2y minus z equals 0? So that should be a plane, shouldn't it? And it is. Right? So you have kind of already seen a 3D function, haven't you? Planes are 3D functions. Space curves are not three-dimensional functions in the usual sense. When you do a space curve, right, when you do an r of t, don't you plug in one variable t and out pops a three-dimensional vector? Do you see that's different? Here, you plug in two values, x and y, and you get back a single dimension. So that's kind of cool. Oh, and guess what? GeoBra takes it for us. So I am going to try x squared plus y. God, my eyesight, I've lost it. Y squared. Oops, careful. Y squared plus z squared. Let's make it equal 4. And there you have a really cool emblem for a sci-fi movie. Yeah. Agreed. Kind of cool. So are you comfortable that you can use something like GeoBra to do some of the questions where it says, here is a function, here are 6 guys, you know, I'm thinking homework, here are 6 guys, who is he? When you just go to GeoBra, type it in, and then look at your guy and look at their 6 and pick it. It's quite difficult to just visualize three-dimensional functions by looking at their formula, right? Some people have got a really good ability to do that, but most of us don't. So I guess my intro then has been, here is a new guy. It's a function of several variables. You can write it in 2 distinct ways. These functions represent surfaces in 3D space, and you can use GeoBra to see what they look like. Any questions so far? That's been pretty cool. I thought the sine of x squared plus y squared was really cool. Anybody into music and have got a synthesizer, tell me what that sounds like. Now, let's look at how you calculate or find the domain of one of these functions, right? So I guess I should stick 3D in. How do you find the domain of a 3D function? Well, let's take some examples. The domain is usable xy's. So the domain of a three-dimensional function are all the possible usable values for the coordinate pair xy. Would you agree in this particular example, you can use any x and any y you like, and this is calculatable? I don't know if that's a word, but I know what I mean, right? You can get the answer. So if you want to write the domain down, there's a couple of ways. There's the way I would do it, which is what I'm about to show you now. Oops. There's actually three ways to do it. First one is you could just say, oops. Okay, let me try that again. I didn't have enough room. You could say that the domain is a set of full values. I'm using set builder notation here, such that x is between plus and minus infinity and y is between plus and minus infinity. But you could do that, that describes quite, it describes exactly what the thing looks like, right? You could give the domain by going minus infinity to infinity cross minus infinity to infinity. You could call it r plus r, or you could call it r squared. Okay, now let's do this one. You see this cross here? It has nothing to do with cross multiplication. It's the symbol cross being used for a totally different reason, right? What that is saying is this represents the usable x's paired with the usable y's. So for instance, if I use this notation and I told you that the domain was 0 infinity cross minus 1, 2, that would mean you could pick any value of x you like that was positive, including 0, and pair it with any value of y as long as it was between -1 and 2, and you would be able to get a value for the z coordinate. Right? So that's what that means. This here is just an abbreviated version of this. I think we all know that that symbol means all real numbers, right? So if I wrote it this notation, it would mean x can be any real number you like, paired with y could be any real number you like. So isn't that essentially everybody? And you know, this one is an even more pared down version of this. So I would always use that one because I'm lazy and I'm a great believer in conciseness, right? If you can say something with a couple of squiggles, or you can say it with a whole load of stuff, I would always go for the couple of squiggles, right? If it means the same thing. So are we comfortable about what a domain is, right? A domain is basically the usable coordinate pairs xy. Let's look at some examples of functions. Sometimes it's easier when you calculate a domain. It's easier to find the things that are not allowed than to try and figure out what is allowed. When will this function have a problem?
When x and y are equal.
Right. So if you want the domain, sometimes you can't avoid it, right? You have to do set builder notation. You see, all I've done is take what's bad and say, don't make it happen. So if x equals y is a bad thing for that, you can see x not equaling y will make it perfectly safe, right? As long as x does not equal y. What about a function like this?
Both x and y together have to be greater than 9 or equal to 9.
Added as well, agreed? So what I mean by that is that doesn't x squared plus y squared have to be greater than or equal to 9? You can't just have x squared greater than 9 and y being anything it likes, because that won't work in some situations, right? Actually, because y could be, well, yeah, that definition would work, except it would miss points, because couldn't x be 2, and as long as y is big enough, it would still be okay? We good? Now let's, oops. Now let's do some weird functions where you have to kind of okay, let's go hunting for bad guys. Is there anything in here that is a bad guy? You just can't use it. If you try to, the function wouldn't exist. Is there any value of y that you cannot use? Just y on its own.
0.
Right. Would you agree in this piece here? Right. You better not make y 0. Would you agree that similar things happening here? You better not make x 0. Right. And we've done this guy in the middle before. You better not make x equal y either, right? So you basically just take your restrictions. And now you've got your domain. So if you have a question that gives you a function and asks for its domain, these are the kind of approaches that you do. Of course, you also get this weird question. Draw a picture or a diagram, I try to think of what word they use, of the domain. And then we'll give you a function. Let's say right, right. So let's look at this guy. Now, if I'm talking about its domain, doesn't this expression have to be positive? And that means then that x squared plus y squared minus 9 has to be greater than or equal to 0. And with a little adaptation, that's the same thing as saying x squared plus y squared has to be greater than 9. And then I'm taking into account that this is 1 over the square root. So can I actually equal 0? So it really should have been greater than 0 and greater than 9. Well, I want to draw a picture of that guy. And the picture they're talking about is that. And the homework question is one of those that gives you 4 pictures and you pick one of them that's right. So let's see what this fella looks like. Do you recognize that guy? Greater than 9 or greater than or equal to, doesn't matter right now. Do you recognize what that would look like if it was equal to 9? X squared plus y squared equals 9. What would that give you in good old 141 days?
A circle.
Yes, radius 3. So far, so good. Now, if you want x squared plus y squared to be greater than or equal to 9, do you mean everybody inside the circle or do you mean everybody that's outside the circle? That's the 2 choices.
Outside the circle.
Right, so you indicate that with the shading. And then, how do you tell people that the boundary is okay or the boundary is not okay? If the boundary is okay, you just draw it like this. And if the boundary is not allowed, you make the boundary a dotted line. So when they ask you to draw a picture of the domain or draw a diagram of the domain, you look at your relationship, in this case, this one here, and you figure out what all the XY values would look like if that was true. And it's normally some kind of shape shaded inside or some shape shaded outside.
What did you say the dotted lines meant?
That meant you're not allowed to equal 9. And in this case, if it was equal to, you'd make it a solid curve. But in this particular question, wasn't it greater than 9? In fact, if I give you right underneath it a different function, with one major exception, really, is that guy. Wouldn't the only difference between the domain of this function and the domain of that function would be the boundary points? And so that one there would look almost identical to what we just did, but you see that the circle would be a solid circle, and this one would be a dotted circle. So a little nuances, but dotted lines have a meaning in these contexts. Are we good? Let's move on to a thing called the contour map. Of a 3D function. Contour maps are always drawn on the XY plane. They're basically drawn on the floor of the shape. And a contour map basically joins all points with an equal height. So imagine they're all 10. And these are all 5. That guy there is 0. And this guy here was 15. Now, for some of you who were in the Boy Scouts, or I know they probably still do it, don't they, in the military, do you recognize contour maps? You know, before GPSs and all that. The military better do this. I hope they do it, especially if you're in the infantry, Marines. You better learn how to read a map, because in times of really bad conflict, won't the bad people shoot most of your satellites down to try and screw up with your communication and with your mobility, right? So you can't get too comfortable with a handheld GPS and all the good stuff like Google Maps, because if the bad guys shoot down all your satellites, you're going to have to resort to pieces of paper. So if it's not a secret, do the military still give you maps with contours on them? Are we screwed?
On a boat.
Okay, there's not a lot of need for a contour map on a boat, I guess. Right, so in your case, I don't know.
A lot of
maybe
the
50.
A lot of the
James?
submarines ended up having contour maps for the ocean charts.
Because of the surface of the floors, the seabed. Right, and they probably look not unlike this, right? They just have some kind of equal line thing, and it gives you ideas of depression and so on. And what this allows us to do in this context of what we're doing is it allows us to try and imagine a three-dimensional object using two-dimensional paper. I'll give you an example. Can you imagine that we're talking about the surface of a cone? Right. And what you will have this cone resting on the XY plane, right? So what you do is that you cut the cone at, say, height 1, then you cut the cone at height 2, and then you cut the cone at height 3. And for each one of these horizontal cuts, would you agree that if you cut a cone, wouldn't you get a circle of a different size depending on where you sliced it? And so you imagine this transferring down here. What you would get is a sequence of equally spaced circles. And these circles would have a little 1 on them, a little 2 on them, and a little 3, and I guess right at the apex, the height would be 0. That would be the contour map. That, I don't know, it looks a bit like a bullseye shape, right? That's the contour map for a cone. So I'm going to give you a contour map and see if you can figure out what its 3D shape, its surface, might look like. So I'm going to have this guy is 5. This is 4. This is 3. And this is 2. And I guess I could do one more. And this is 1. So you're looking at a map of the ground, which is probably a good analogy. What kind of shape would generate 5, 4, 3, 2, 1, for instance?
Dome?
Say again?
Is it a dome?
No, not yet.
It's a
Oh,
cone, most likely.
yeah. Can I tell you that these are meant to be equally spaced, even if they don't look equally spaced? That might be a clue.
It's most likely a cone sticking up out of the ground.
So you would think like this?
That, but in the cone is flipped. The base is at the bottom because the base is the lowest one. So because one I'm presuming denotes the lowest elevation. So
Correct.
1 is at the base, and then it's going up as it gets higher. So it's a cone coming out of the floor. Yeah.
Okay. Yes, it is. So can you imagine this cone represents that one, and then you imagine another cut, that would be at 2, and another cut, and that would be 3, and another cut, that would be 4, and that pinnacle point would be 5 off the ground. Can you see that if you focus on a contour map, it is possible? Now, the fact that they were meant to be equally spaced is why you get a cone. Now I'm going to try and draw another contour map. What do these questions look like? You can almost imagine how the homework's going to be. 1 contour map, 4 surfaces, who am I? Right. Right, let's have a look at this contour map then. So we'll make that guy 0. Then I'll do a circle at 1. Then I'll do circle at 2. And then I'll make a bigger circle at 3 and the yikes, okay. A bigger circle at 4. These circles are not evenly spaced, right? From 3 to 4 takes a bigger chunk of space than 2 to 3. That's what I'm trying to draw here. I was never an artist, as you can see. So I want to try and imagine what this shape would look like. And I think someone kind of mentioned it earlier when they were looking at one of these shapes.
It's kind of a dome-ish depression where it's not quite a point at the bottom, but it kind of spreads out as it gets higher. And
So it's here, and it kind of goes like this, but oh God, I can't draw it. This just share something with you. I'm a very visual person. In my brain, I can see a pretty decent version of what that looks like. I got a good picture. I can move my hands like it. But when the signal goes from here to here, it just totally disappears.
The distance between each elevation interval denotes the slope. So as it gets farther out, it's going to lose a lot of its slope. So it's a lot steeper towards the center, and then as it comes away from the origin, it starts to become less of a...
Very poor attempt at it, but yes. And the good news is that when they give you the shape, there's only one going to look like a soup bowl, right? And that's probably a good analogy, right? A soup bowl. It's kind of what my brain is saying, right? It goes kind of, whatever, right? So are we comfortable that you could take a shape like this and reconstruct in your head roughly what the surface would look like? And it's not that difficult actually to do the reverse, right? If you've got a solid shape, wouldn't it be a little bit easier to imagine what the contour map would look like? So you're going to have questions where they give you a shape and then they say which of these 4 contour maps would match it. And then the other kind of question is the reverse of that, where they give you a contour map and they give you, 4 shapes. One of them will be this, one of them will be that, and one of them will probably be, that guy upside down kind of thing. And one of those 4 shapes is the right one. Are we cool? If you switch numbers and you make that 4, 3, 2, 1 instead of 1, 2, 3, 4, what will be the net effect to the shape? Because it won't actually change the shape that much, will it?
It'll be inverted.
Yeah, it'll be, instead of going this way, it'll go that way, right? It's a bit like somebody takes the shape and just turns it upside down and right inverts it. So similar contour maps with different numbers. If they do not tell you the numbers, isn't there 2 possible shapes to it then? The bowl of soup up the way or the bowl of soup down the way, right? Which would make that question a little bit unfair then. Unless there was only one shape that looked like a bowl of soup, right? In which case it would be, you'd pick that one. So far, so good? I'm just picking some bits and pieces while we're at this. Suppose I had a function f of xy equals x squared minus 2xy plus y squared. And this is really just for completeness sake. Somebody said evaluate it at 1, 0. Well, you know the convention, that makes x and that makes y. So wouldn't you just go 1 squared, take away 2 times 1 times 0 plus 0 squared, and the answer would be 1. I don't really think there's much else I need to say about that. Isn't it pretty obvious how you would evaluate a function at any given point? You just replace the x with whatever it is, you replace the y with whatever it is. But have you noticed that when you plug in an x and y, doesn't this always become a number? That's why it's a function in this case, x and y. I'm going to see if, for a few seconds here, I'll see if I can get into WebAssign. I think Canvas, at least for the last person who came in, is still not behaving, so I'm not even going to try that in case it...
I just got a text from OC. They said that they had a power outage, so I'm willing to bet that dropped their server.
This thing. Okay, it's not their fault. You can't plan power outages. Okay. So, okay, we are in. I'm just clicking on this, getting it ready for you, so you can. you know, see what kind of questions are expected of you. So you can hold off for a few seconds. Right, so I'm going to go in and we'll see what this thing looks like. Right, here we go. Oh, darn it, I don't want solutions. They distract us. Okay. Well, here's a function. Evaluate g of 6 comma negative 2. Can you imagine the answer to that might be the cosine of 15? What would that be? In fact, that would be 6. And so, oh, it's a cosine of 0. Okay, cosine of 0 is a nice number. But can you imagine in other combinations it might be the cosine of 15? If it doesn't say to 2 decimal places, will you write down the ugly answer? Cosine 15. And we're talking 15 radians here, not degrees, right? So that would be it. Now, in this story here, what is the domain of this function they're calling g? What are the usable xy combinations? Well, let's look at the function. Can you use any x and y you like in the calculation x plus 3y and you'll be fine?
Yes.
Can you find the cosine of 1 billion and the cosine of minus 1 billion and the cosine of any normal number that you could possibly think of? Then doesn't that make the domain r squared? Remember my abbreviation, minus infinity, you know, paired with plus infinity, that one, r squared is convenience. Now, what is the range of this function? Now, the range of the function is what's the biggest and smallest value that the cosine of x plus 3y can be. And we're going to use interval notation for that.
0 and 1.
Oh, half right. Fix it a little bit. You're almost there. Yeah. I think I interrupted you as you were fixing it.
-1 and 1.
Yeah. Oops, it helps. I think what happens to people is that when things are inside cosines, it screws with their brain and they suddenly think that the cosine function can become bigger than 1 or that it can never be less than 0. I guess in some circumstances that might be true, but not in this situation here. For the vast majority of things, I don't even pay much attention to that bit in there. What a cosine between -1 and 1 is kind of what you get no matter what you stick inside it. Here is a guy. What you would do if you weren't sure, and I can understand why you might not be, is couldn't you go to that GeoBra or Desmos and plug it in and have a little look at it? But since I don't have the features of doing that, and I don't want to, there are only 4 guys here. Top left and right, bottom left and right. One of those 4 guys is z equals x squared.
Bottom left.
That one? I agree. Tell me why.
Yeah, explain.
Oh, okay.
The
X squared is
would
a
make it a longer.
parabola.
Uh-huh.
The top
Why is it
right
not that?
one's-
Right. Well, why is it not that one?
That one's along the y-axis, so that would be it if it was y squared. But because it's x squared, it should be along the x-axis.
Good answer. Right? We cool on that? I mean, you can use GeoBra, but if you can see it, it's just so much better. To be honest, I can't see this one, so I'm not sure myself. Let's see if I can visualize it just from the information. It looks like you start with a big value and then you take away stuff. So that should mean that at the origin it's taller and then it disappears downwards. So my gut feeling would be it would be that one based on just that very crude approximation. This one here's got some weird bends in it, which could happen. So is this one. So, but I'm definitely not picking that one. And yeah, can you imagine just going to GeoBra and having fun and seeing what some of these surfaces look like? Well, let me kill some guy. See this fella here? It's in a square root. Doesn't that make the Z values have to be positive? So I'm going to kill that one. Would you agree this shape here has some Z values that are below the XY plane? So that one's dead. I'm killing that one for the same reason. So now I'm down to, whoops. Now I'm down to a kind of process of elimination. Either this one committed the crime, right, or this shape committed the crime.
Bottom left.
Oh, interesting. Why? I'm not saying you're wrong. I'm just trying to get your thought process of why.
The 4x squared minus the y squared, it's a scalar of the y component.
Oh, interesting. Oh. Yes, yeah. Yes, my different way of looking at it, and I'm totally cool with your way of looking at it. Do you know what I would do with this shape here is I would choose a value for this to be 0. Now what that would do is it would project the shape onto the floor. So I'd be looking at what does the surface do when it hits the XY floor, or at least as close to the floor as it could get, right? Well, if you're looking at that shape there, do you see that shape there when you make it equal 0 as an ellipse? Isn't 4 take away 4x squared minus y squared essentially 4x squared plus y squared equals 4, and that's an ellipse. So I was looking for the shape that had an ellipse, which is that shape there. I'm not really convinced that that's obviously on the floor, but it probably should be. And this one here is, it's a cool question, but you're really going to have to get good practice at GeoBra. I'm sure I have put a link somewhere in Canvas once it works for you to go either to Desmos or GeoBra, and you plug the guy in and you look at it and he's one of these shapes. I could try one at random. Okay, see this guy E, f of xy is the absolute value of xy. Okay, let's see what kind of clues we've got here. Would you agree that because it's an absolute value, the z coordinates have to be positive and above the plane? Right? So I guess that kills 4, doesn't it? I'm pretty sure it kills this one here, which is 2. I'm not sure about that one, so I'll let that one slide. Anyone want to have a shot at it? Which one of these shapes is the absolute value of xy?
3.
So you're looking at this shape here. Okay, let's see. Absolute value of xy. No, but I took me a while to figure out no. Why? Well, here goes. If you take if you take the point x comma y 0 0, won't the z value be 0? So don't I want a point that is at the origin, right? At 0 comma 0 comma 0. And so because of that, I can kill this one, this one, this one, this one, this one. Oh, by a process of elimination, it had to be 6. Kind of cool. Yeah, kind of cool. Here are some contour map stories. Here's a contour map. One of these pictures match it. They're really making it easy for you. You see these lines that they put in the ship? They're basically points of equal height. So can you imagine what this shape would look like if you did a contour map? Wouldn't it be squares inside squares inside squares?
Yeah.
Right?
It should be the top left one.
It should be, shouldn't it? If you did this one, wouldn't this just be a sequence of parabolas? Going like this? Yeah. So I'm going to assume that you can do that. These 6 here are going to be fun. So I'm going to pick one, E. I don't know if you can see it. It's probably quite tiny on your screen. But do you see this one that looks like a whole load of eggs in an egg box? One, right? E. Which one of the contour maps, and these are quite detailed contour maps, would generate picture E? 3? All agree? Right, there were clues in that. To me, aren't the clues lots of concentric shapes that look the same? So wouldn't you expect a contour map to have a lot of symmetry based on little shapes getting higher, which tends to be what? Consecutive circles or whatever the shape might be. Yeah. What do you think A is? Which number is A? I'm pretty sure I've got a feeling for it.
It looks like 1.
Oh.
E looks like number 3.
Oh, we're getting all sorts of other answers, but not the one to my question. E looks like 3. E looks like 3 is we've agreed on. What about A and 4?
Four looks like it's number or letter A. As it gets higher as it goes to the side.
And it has a kind of curvature thing going on, doesn't it? So you imagine when you slice it, you get lots of curves. Now, the guy that looks very similar to it is 1. Do you see that 1 has a kind of symmetry, but the symmetry is very linear?
Yeah, that's going to be F.
That would be F. Now, one of the problems we have, and it's coming out really well on this question, is do you notice that the orientation of X and Y is not the orientation that you use in 3D pictures? You have to kind of turn them like 180 degrees to see them. And so things point, for want of a better word, in the wrong direction. Do you see these consecutive bands are all pointing this way? Do you see in this shape they're all pointing that way? But that way is this way when you orientate the X and Y the way that humans do that. No one in their right mind would do this, but do you know, to make 3D calc easier, shouldn't we have done coordinate systems where the X and Y axis were drawn the way they're done in 3D? Now, can you imagine how weird that would look to you if you were starting your math career? So I know why they didn't do that, but it would have made life a lot easier at the end, wouldn't it? Because we get used to functions looking a certain way. But anyway, we got them. And here are lots of shapes and lots of functions, so that's kind of fun. And now we're on to sketching domains. Now, here is the function. There are only certain values of X and Y that you can plug into that and get an answer. Would you agree that this here says that Y has to be greater than 0? So won't that kill this and this, the two right-hand pictures? Why do they get killed? Because don't they have negative Y values in them? So now we're stuck with this guy and this guy. Right? Well, if you look at the square root guy, do you see that that's basically all the points on and inside a circle of radius 6? So that makes it this one. Now, you won't have any GeoBra to help you here. You've got to figure that out on your own. I'll try this one. So this is back to surfaces. Y squared plus 10. So the Z coordinate doesn't care what the X value is. It can be anything it likes. It then takes the Y coordinate and squares it, and then it adds 10. Who are you looking at here? Top left and right, bottom left and right. This you could do in GeoBra, by the way, or Desmos. I see some nods, but no volunteering answers.
Looks like bottom left.
It is bottom left. Right, now if this was in GeoBra, I would rotate it. And what I would do is I'd rotate it a little bit so it's face on. Can you see that if you look at this axis here, it's Y, and you look at this axis here, it's Z? Isn't that a bit like Y equals X squared plus 10? But in the orientation and the variables, it's the same as Z equals Y squared plus 10, right? Y is the predominant independent variable and Z is the dependent variable, right?
Professor?
Yes.
So since this one y squared plus 10 makes it along the x-axis, would it make the x squared on top on the previous problem, wouldn't it be along the y-axis?
Yes. Did I say something wrong? I hope I agreed with what you just said, because it would be correct.
Okay.
Right. So if this had said x squared plus 10, can you imagine this shape being just rotated 90 degrees so that the y-axis would be like the spine, but it would be x-axis going sideways and then curving up? It would have the very similar shape, right? It would just be rotated 90 degrees in a clockwise direction.
Okay.
Okay, that's the end of those questions. I think they were pretty straightforward for the most part. And you're going to have, I like it. I like using, 3D graphing software because it's just kind of fun. And hopefully that won't cause you too much grief. So where we're off to next is, we're going to look at limits and continuity. Right. Oh, let's start. Yeah, that'll do. Do you remember Calc 1 and doing limits? I know it's a long time ago. One of the go-to techniques for finding limits is called L'Hopital or L'Hospital, whatever way you want to pronounce it. There was other techniques, wasn't a technique called factor and cancel? When the limits were infinity, didn't you do a technique called brute force? Basically, 1 over infinity would get you 0, things like that. So if you were asked to do this fella, you would look at this particular expression and you could certainly try and evaluate it. But the natural log of 0 is a problem, isn't it? Because the natural log of 0 is negative infinity. And then if you take negative infinity and divide it by 0, you would get a really, really bad answer, right? Something that you wouldn't want. But basically, this answer here would be negative infinity. Now, if I wanted to do a guy like that, I could do L'Hopital, couldn't I? If I chose to do L'Hopital, then we do the limit as x tends to 2 of 2x over 1, and that would get you 2 lots of 2, and so the answer is 4. If I switch places, in this case here, I differentiate that guy, and I differentiate that guy, which means I'd be looking at the limit as x tends to 0 of x, and the answer in this case would be 0. I guess technically negative 0, but isn't negative 0 the same as positive 0? It's still 0. So, how do you find limits? of multivariable functions. I wouldn't call them functions, I'll call them expressions because that allows you to do more things. For instance, what's the limit as xy tends to 1, 2 of x squared plus y squared over x squared, take away y squared? Well, there are a number of techniques. Technique 1, which is very often overlooked, is you can evaluate. Do you know if you can plug in the number and you get an answer, isn't that the value of the limit then? This one, you can take 1 and square it, and 2 and square it, and 1 and square it, take away 2 and square it, and you get 5 over -3. I guess I should put the negative in the middle. The limit would be -5/3. Great. How about the limit as xy tends to 1, 2? Well, actually, I'll make it 1, 1. It'll just make my life easier. Of x squared take away y squared over x plus y. In fact, let me change that again. More interesting. X minus y over x squared minus y squared. Right, now if I try to evaluate it, won't I get 1 take away 1 over 1 squared take away 1 squared? Won't I get the dreaded indeterminate form? Agreed? Here's the big problem. L'Hopital has left the building. You can't use them. How do you differentiate x minus y or x squared minus y squared? Now, you may come up with quite creative ways of doing that, but none of them work. So we are going to use method 2. Depends who you got, but if you got me, I call this method factor and cancel. So we're going to look at the limit as xy becomes 1, 1. Top guy is that. Bottom guy is that. And we're going to factor. Okay, can you factor x squared minus y squared? Sure can. Do you know what it is equal to?
X plus y, x minus y.
Yeah, isn't correct. Isn't it a difference of 2 squares, everybody? Did you think that factoring had left the building? That you would never need to factor another thing in your life? Because that was then and you're on to cool stuff. No. You will never not be factoring things in your advanced math career. Factoring is like adding, right? You can't avoid it. It doesn't happen a lot, but it does happen. So, difference of 2 squares. Now, can't you then cancel? Remember to leave behind a 1. And so what we now have is the limit as xy tends to 1, 1 of 1 over x add y, which is 1 over 1 plus 1, which is 1/2. So we can evaluate and we can do factor and cancel. At least they survived the journey into multidimensional functions, right, or multidimensional expressions. That does exist. Is there any other techniques you used for finding limits from Calc 1? Okay. You remember a guy called the conjugate method? It had square roots in it, didn't it? And it was a pretty rare technique. You probably only got to see a couple of examples of it, but it did exist. So let me show you the situation where that might be necessary. Now you're going to have to bear with me for a little while. I want to make ones that come out at least nice. Let's make that the number, then I can make this happen. Okay, I just need to make this 16. Am I going to get 16 out of this? Darn it. Okay, make that 3. Can I get 9 out of that? Yeah, I can do it. Okay, got a question. So limit is x, y tends to square root of 2x minus y, take away 3. And I'm going to be choosing, got a 1 there. I'm going to choose 4 and 1. Gotcha, right? And on the bottom, I'm going to go x plus y, take away 5. So in this question, if you plug 4 and 1 in here, you get 9. Square root of 9 is 3. 3 take away 3, 0. And 4 add 1, take away 5, 0. Do you see you get the dreaded indeterminate format, right? Now, when you do the conjugate method, so I'll have to rewrite this guy again. And I'm just going to write the word limit ... so I don't have to keep writing that all over the place. When you do the conjugate method, isn't the trick to multiply by a special version of 1 called the conjugate? That's where the name came from. And it was made up of these two guys here. And it looked just like them, but it didn't have a plus. Is it ringing bells, this technique? Now, how's that going to help us? Well, it's going to be square root of 2x. Oh, Start again. What do you get if you multiply the square root of 2x plus y minus 3 and the square root of 2x plus y plus 3? Aren't they a difference of 2 squares? So don't you get the first guy squared, take away 9? So what do you get out of that? You get a 2x plus y, take away 9. Do you see the square roots have gone? Now what do you get on the bottom? Well, you get an x add y, take away 5. And the square root of 2x plus y add 3. And you're going to have the limit as x comma y becomes 4 comma 1. And let's see what we get now. Well, if you plug 4 comma 1 in here, you get 2 lots of 4 plus 1, take away 9. What have I done wrong? Oh, I know what I did wrong. I generated the bad value at the bottom. Okay. Don't make questions. I keep doing that same mistake. I'll tell you what should have happened in a better choice of question. See this guy in the top here? I would have had that guy in the bottom. So imagine I put that guy in the bottom. Then this guy here would have cancelled out with that guy there. And I would have had the limit of xy tends to 4, 1 of just this fella. And that would have ended up being a sixth. Okay, so what should have happened is I should have changed that bottom one to this fella all the way through, and it would have worked. So there are three main strategies for evaluating limits. Plug them in and get an answer. Factor and cancel if you can. And if you see some square roots, be on the lookout for the conjugate method. And those are the overlap methods that we got from Calc 1. Now we're going to have to look at something that's new that you would never do in Calc 1. And a lot of these new questions revolve around xy becoming 0, 0. And they also tend to be polynomials, so you'll recognize them when you see them. Right, in this case here, if I plug 0 and 0 in, would you get the dreaded 0 over 0? So we're going to have to try and figure out, most of these times it has a problem. In other words, the value of this function is undefined at 0, 0, right? It has no answer, right? And so we're going to go hunting for it if it did. So what you do is you choose a path. Actually, you choose two paths, but let's choose a path first. And the typical path is you choose the path x equals 0. So if I take this fella here and I say I'm only going to make x 0 and I'm going to make the y tend to 0, right? So you imagine xy becoming 0, 0. If I said, let's just make x 0 all the time, what I'm doing is I'm traveling along the x-axis towards the origin, right? That's one of the pathways. Can you imagine that you've got your xy here? Essentially, I'm trying to find out what the value of the function is, starting here and moving to there, right? Because wouldn't that get me 0, 0? Now, if I choose to do that, then this limit becomes, the limit is y tends to 0. That gets you nothing, right? 5 nothing squares, I'll put it in, I guess. 5 nothing y plus y over 2 nothing y plus y squared, which becomes the limit as y tends to 0 of y over y squared, which is the limit as y tends to 0 over 1 over y. Would you agree that 1 over y is undefined? We know it's probably going to be one version of infinity, but we don't go into the details. That means that this function has no limit. And by limit, we mean no numerical limit, right? It's not equal to a number. I'm looking for some, what on earth did he do faces, or, okay, I get it. He's doing some kind of cheat thing. Right. Well, let's do one where you don't get infinities, but there's still a problem. Let's do 3xy plus 2x squared over xy squared plus 3x cubed. Oh, not 3x squared. 3x squared, fixed end time. Right, let's choose a pathway. Let's make this a bit more interesting. Yeah, okay. Let's choose a pathway. Let's choose x equals 0. Now this question would then become the limit as y tends to 0. Now if you make x 0, won't you kill that guy off, and you're left with a y? And won't you kill that guy off, and you'll be left with a 3y? Oh, wait a minute. Doesn't that just become the limit as y tends to 0 of a third, which is a third? So I got a number. So you might think, oh, the answer to this is, it's a third. No, unfortunately. I'm now going to choose another pathway. And the second pathway is going to be, I'm going to choose to make y equals 0. Now, if you choose y equals 0, your limit now becomes the limit as x tends to nothing. If y equals 0, that disappears. If y equals 0, that disappears, and you're left with 2x squared. If y equals 0, that disappears. If y equals 0, that disappears. And we're now with that fella. And that gets me the limit as x tends to 0 of 2/3, which is 2/3. Aren't these two different pathways to the origin, right, to 0, 0? But if you travel along this pathway, the z value is a third. And if you travel along this pathway, isn't the z value a totally different number, 2/3? What does that tell me? It tells me that this limit does not exist. Now, can you imagine a situation where this pathway gave me a third and the second pathway also gave me a third, right? Can you imagine that could happen? What do you think the conclusion might be in that case?
That the limit exists?
And that it's probably a third, right? Which would seem totally reasonable and unfortunately totally wrong. If it was intuitive, it should be right, right? It just should be right. So why even doing two pathways, x is 0, y is 0, and everybody agrees, why that might not be wrong? Well, it's because you can choose all sorts of pathways. Couldn't I choose the pathway to make y equal 2x? In other words, I'd be traveling along the line y equals 2x of the origin. These two guys might agree. Do you know this pathway might not agree? Let's see what this pathway, I know this one doesn't work, but let's just imagine this, that these two were equal to it, right? In fact, let's do that. Let's see if I can make something happen. So if you did the pathway to the origin, and I'm going to have to create a new question. So I want both these to be the same, and then we're going to see what happens if I choose this pathway. So I guess if I keep things simple, that'll probably make my life work a lot better. Can you trust me that if you do the first pathway, you get 0 if you choose the second pathway, right? So if you make x equals 0, you get 0. And if you make y equals 0, you get 0. Let's see if I can, maybe 0 is a bad choice here. Could get that. Okay, we'll go for it. Right, so would you agree in this case, the pathway along 0 said the limit was 0, the pathway along y says 0. I'm now going to choose a weird pathway. There's nothing significant about the two. Do you know I could have said y equals 5x or 2x or anything x I felt like. Now what's that going to look like? Well, it's going to look something like this. It's going to be the limit as x tends to 0, and I'm going to replace all the y's with this fella. So instead of y squared, I'm now going to have 2x squared, and instead of y, I'm now going to have 2x. And that guy there is going to get me 5x squared, and that guy's going to get me 3x, and darn it, it is going to be 0. I can fix it. There you go. I just turned them upside down, right? Go through this one. You get x add 2x, x squared, 2x squared. That gets you 3x over 5x squared. That gets you 3 over 5x. What is going to happen to that fella when x goes 0 on you? Because you get undefined. Now, if you switch these guys around, can you trust me, you still get 0 and 0. It still, hopefully it still works. The moral of that story is that you can use the technique of pathways to prove something doesn't have a limit. It's not very effective in proving that it does have a limit, because maybe the pathway along x equals 0 is the same number as the pathway along y equals 0, but couldn't the pathway along y equals 10x get you an undefined or a different number perhaps even, and you know, throw you for 6? Are we good? Okay. So where am I going? I think. What's the time like? Yeah. I think we have time to have a look at our second set of homework. That'll give me a chance to figure out if I've missed anything as well. So we're going to be looking at section 4.2. Right, so there is things I haven't done, that's fine. Oh, I'm getting worse. Okay, should be looking at limits. Okay. Find the limit if it exists. If the answer does not exist, enter DNE. Okay. Question 1. Any ideas about possible limits here? If you do the pathway, can you trust me here? I'm just doing it in my head. But if you make x equals 0, the limit ends up being -2. If you make y equals 0, the limit ends up being 0. Do you see that they disagree? So that's a DNE. Do you want me to do that one, or do you see what I'm getting at? Right, if you make x equals 0, right, won't you just be left with 16y squared and 8y squared, and that cancels down to give you a number -2? And then if you swap places on it and you make the y 0, don't you get an x squared over x squared, cancels down to x squared, you make that 0, you get 0. If you use two different pathways and you disagree about the limit, that simply means the limit does not exist. Okay. Now, if you try to do question 2, if you did the pathway x equals 0, if you did the pathway y equals 0, can you trust me that in both cases you get 0 as the answer? Right? In fact, since that one's there, let me actually do that one. So it's going to be the limit as xy travels to 0, 0. And it's going to be xy over the square root of x squared plus y squared. Now, I'm going to prove to you that that does not exist. So here it goes. If you make x equals 0, right? So if you choose that pathway, your thing then becomes the limit as y tends to 0. Right, if you make x 0 here, you get 0 on the top. You make it in the bottom, what you're going to get the square root of y. Would you agree? Oh, you probably shouldn't agree on me, this one. You get it doesn't exist. Zero, it ain't a guy that you're going to go, I thought that one was going to come out nicer. That's a pity. Back to where we were then. What do you think of 4? Another DNE? Yeah, pretty sure it is. In question 6, go into Desmos or GeoGebra and look for discontinuities. Okay. What does discontinuities look like? Let's try and show you a discontinuity. If you had a function and it was just that guy, wouldn't there be a problem at 1? What kind of problem at 1 would you get? You get some kind of vertical asymptote, at least in the 3D world, right? It would be, yeah, it would go like that, right? If you stick a square in it, wouldn't it look like a volcano, right? Now, if you made it into a more likely equation, right? A 3D surface like this, that would be a discontinuity, right? It would look something like this. Me and my bad artistic skills. Can you basically imagine an infinite volcano? It would have a discontinuity. So discontinuities, when you put them into GeoGebra, will be volcanoes shooting off to the, infinitely up, or big holes in the ground like a gravity well, especially if you imagine the black holes at the center of the gravity well. And then you get these kind of, do you know how you have a curve up and a curve down? Can you imagine a surface curving up and then the surface curving down? What you get there is a discontinuity which is made up of an infinite line of points where bad things happen. An example of what I just said would be that function. Because along the line of points, y equals x, can you imagine on one side the curve goes up and the other side the surface curve comes down? That's what discontinuities look like. It's different in the 2D world. Don't most discontinuities look like jump discontinuities? And occasionally, vertical asymptote discontinuities. And there's a really weird one, isn't there, where you get a removable discontinuity. Do you think you can get that in 3D? Yeah, kind of looks like that badly drawn picture, right? Can you get jump discontinuities? You can in a way, but they're pretty rare. Can you get a removable discontinuity? Could you imagine a function that has a removable discontinuity? Yeah, it is possible. A function that might have a removable discontinuity might be something like this. That function has a removable discontinuity all the way along that set of points. If I did this fella, now that would still have a discontinuity. Oh, boring. Really boring function. That one would have a single discontinuity at the point -3, 1. You can get them, but hard to create off the top of my head. So a discontinuity is a point on the XY plane that you cannot use to evaluate the function. So there's places on, essentially, there's places on the floor that if you try to find the height, right, the Z value, it would not exist for some reason, right? It'd be some version of infinity, for instance. So if I return now and see if we've got a few more questions before we run out. Okay, look at question 7. What are the places where bad things happen? Would you agree that functions, bad things happen when the bottom is 0? You can't really do much to the top, the numerator, but you can do damage to the bottom. Would you agree that whenever x squared plus y squared equals 4, isn't the bottom going to have problems? So you would describe, this is set builder notation, you would say that the function is continuous, right, usable, right, as long as that is not equal to 4. Would you also agree that that's the same thing as the domain? So in a kind of way, aren't they just saying what is the domain of this function? Because it's really the same set of values, isn't it? Where a function is continuous isn't, for the most part, where a function's domain is. If you were doing question 8, can you trust me that that's an evaluate? Great. If you were doing a question 9, that would be an evaluate. What about question 10? Do you think you have a problem at 0, 0? Okay. Now, let's prove to you that's a DNE, because I can do that pretty quickly, I believe. Shooting space, I can't. If you make one of them 0, do you know if they've made both of those guys 4, it would have made my life so much easier. Can we pretend that it says x to the 4 minus y to the 4 on the top, just for argument's sake, so I can do what I was about to do, right? If you make x equals 0, won't you have negative y over plus y? Won't that be negative 1? And if you make the y 0, won't the limit be 1? Do you see the x equals 0 pathway is different number from the y equals 0 pathway? That would be a DNE, right? Now, if you do the pathways in this question here, they both end up being 0, right? You have to choose a pathway like y equals 2x or some kind of pathway to see what happens with that one. And if you're really lazy, which I probably would be, couldn't you plug that into GeoBra and look at it and see what's happening at the origin? And if really weird stuff is happening, it doesn't exist. And if it looks kind of smooth, you know it's a number. In which case the number would be 0 because you've already found it with the pathway. Okay, determine which points are continuous. Would you agree it's just a matter of finding out what values that is allowed to be inside the log? And there's a whole bunch of questions that shouldn't be there. They should be in the next section. But that's fine. I'll get that fixed before you get there. Right, now I'm going to take an attendance thing here. I kind of had to wait, I think, to be fair, because of the Canvas issue, for everybody to be here. So it's gotcha. So the questions that you've done on limits are finished, and the intro is finished. So what is left for the rest of this week? Well, let's give you an intro to it. I've lost you. Oh, here we go. How do you differentiate functions when they're multivariable? So the last part is going to be 14.3, and it's called partial derivatives. You're probably going to be in one of two camps. Hopefully all of you will be in camp one. Hey, no biggie. I know how to differentiate. There's a different rule, but apart from the special rule, I'm differentiating in multivariate questions. When you differentiate, they're called partial derivatives, right? It's pretty much the same. And then, unfortunately, some of you are going to think, that just is weird. I can't get my head around it. And you're going to have to work on it, and eventually you will get your head around it. So let's give you an example of what we have. If you take this function, I'm writing in both its versions, you end up with a surface that looks a bit like that kind of thing, right? Okay, can you imagine that? It's I don't know, what's it look like? It looks like a monk's cap turned upside down. It looks like a bowl of soup, kind of bowl. That's what it. Say again?
It looks like a half a globe.
Oh yeah, like half a sphere. Yeah. So you get the gist of it. Now the problem is, how do you differentiate that? Well, before you even ask yourself that question, you have another question. Who's the variable? That's the problem. When x is a variable, don't you differentiate with respect to x, which is what you typically do in Calc 1, right? There isn't an issue, because y is the dependent, x is the independent. You always differentiate with respect to the independent, right? You differentiate with respect to x. And don't we have all the rules of derivatives to help us? Quotient rule, product rule, power rule, you name it, we can do it, right? And we even later on did implicit differentiation, which is how do you differentiate it when the x's and y's are all jumbled up, right? But in this case, there are two variables. X and y can take on any value they like. Isn't z dependent on what x and y are equal to? That's why z is called the dependent variable, right? It depends on what x and y are. Which means that there isn't a derivative to this. There are two derivatives. One where you make x the variable, and another one when you make y the variable. And we call them partial derivatives. And we have a different notation. Can you remember in Calc 1, one of the notations for derivative was a d, and you called it dy dx. Didn't that mean the first derivative, right? Great. The notation that we're going to use is that guy. And the other is that guy. And you read these out as the partial derivative of z with respect to x. That would be the formal way. Most people just say partial dz by dx. You just stick the word partial in front. And this guy here, can you imagine it would have exactly the same, except at the end with respect to y. So here is my z, x squared plus y squared And we have to figure out what it means to get the partial derivative. Well, we have to figure out what to do about the other letter, and I'm calling it a letter now for a good reason. What we do with the y squared. Now, if I am telling you that x is the variable, right, with respect to x, then what we mean is that everybody else gets treated as if it is a constant. So that means y gets treated as if it was a number. And if you like numbers, think of y as being 42 and do what you would have done if it had been 42. So let's see what happens. If you differentiate x squared with respect to x, don't you get 2x? If you differentiate the constant y squared, don't you get the derivative of 42 squared? But wouldn't 42 squared be nothing? And so you get 2x. Now, if you do the partial derivative with respect to y, you get the partial derivative with respect to y of this fella is treated as a constant, gets you 0, and this guy gets you 2y. And can you see in this case, the partial derivative is not the same? So you might be thinking, what the heck am I calculating? Well, what you're essentially doing when you say x is a variable and y is treated as a constant is that you're slicing the shape vertically through different values of y. So can you imagine you're taking this shape and you're slicing it at y equals 5, y equals 4, y equals 3, y equals 2, y equals 1. Now, every time you slice this, don't you basically just get a normal parabola that you would get in the, z equals x squared kind of shape to it? Right. That's what you're essentially doing. So the trick to partial derivatives is just to have a mindset that at any given point in the process, one of these two is a number. It's treated as a constant. And as long as you can do that, the rules of Calc 1 apply really well. So let's up the ante. Suppose it's 2x squared plus 3y squared plus 4xy, right? And I want to find the partial derivative with respect to y. So y is a variable, x is treated as a constant, right? Will I get anything out of 2x squared then?
No.
No. Eventually you're not going to write zeros, but for the sake of notes, I'm going to write it for a little while longer, right? Would you agree that for this guy, differentiating partial derivative with respect to y gets you the good old-fashioned 6y? Now you have to be really careful. This is the first time we've dealt with it. 4xy. Treat x as a constant. Don't treat it as 0, treat it as like 42. So that's like 132y, isn't it? Now what do you get if you do a derivative of 4xy with respect to y?
4.
4x.
Not just, you get 4x.
Mhm.
He's still there, isn't he? So don't get caught up with x's disappear. It's not that unusual, you would expect, right? That there's going to be some x's and y's in a partial derivative, right? Depends on both. How about this fella? Let's do a partial derivative with respect to x. So this is going to be a chain rule, isn't it? Sine of something. Let's see what we get. You differentiate the sine, you get the cosine, right? And then when you finish with times, what's the derivative of x squared y cubed with respect to x?
2xy cubed.
You see the y cubed still there? Y cubed still there. So I would do this guy by making it look pretty, by rewriting it like that. Let me, yeah, just let me, excuse me, finish off this last one. And I'm just changing this question a little bit. But sometimes a little bit can make a big difference. Now, still a chain rule, very similar function. So you're still going to get the cosine of x squared plus y cubed times, what do you get if you differentiate x squared plus y cubed with respect to x?
2x.
2x.
You see the y cube's now 0, gone. Do you see how it lived in this case, but it disappeared in this case? It lived in this case because isn't it like 42x squared? It's still there, it doesn't disappear. But x squared plus 42 cubed, right, disappears on you. So in this case, you would put it together. So that's just a taster. We'll be spending 2 days, and that's going to be tomorrow and Thursday, on nothing but getting you good at differentiating partial derivatives. So it's going to feel a little bit like Calc 1, but there's always there's quite a few kinks that you've not seen yet. So why would you want to calculate partial derivatives, and do they have any relevance to geometry that can help us? Right, can you imagine my shape was this fella? Isn't there a local max at the top of that shape? Wouldn't it be nice if we could find where that was? Now, in Calc 1, don't you just find out when the derivative is 0? Well, what you do in Calc 4, because we don't go that far, is you find out when both of those are 0. Right, so you find out for what value of x and y are the first and partial derivative in the second. So can you imagine the first one might be that guy and it has to 0, and the second one might be that guy and it has to be 0, or let's put a 5 in there, right? Whatever, right? Can you see that if you solve those two equations, then won't you be able to come up with the single point x comma y where both partial derivatives are 0? Because what you're essentially doing, you're slicing this way. Aren't you looking for a hill? So you're looking for a 0 derivative, right? And then you slice it right angles to that. Aren't you also looking for a 0 derivative? When they two meet, isn't that where a hill or a valley probably appears? Right, 0 derivative in this direction, 0 derivative in that direction, right? Make a little cross. That's where hills live. Also, that's where valleys live. Strangely enough, there's other shapes that live there as well. But that's for Calc 4, not for us. Well, if you're interested in your grade, I didn't have any time yesterday because I was given 3 exams. I have another class to teach. I've got a little bit of gap between this and my evening class. In my evening class, I'm getting a midterm as well. So my goal is to get it done by Thursday. So before you get to the weekend, I should have it. Superficially, because I have scanned over them because I was just curious. Things are looking good for most of you. So if you felt good about it, you probably did well. Some of you always feel bad, and then you get pleasantly surprised. I guess that's just the way your brain works. That works too. So that is us. And it's goodbye from me. Anybody got questions or wants to hang about, feel free to do so. Bye-bye, James. Bye-bye, Ken. Bye, Odd, Matthew, Nick, I think Olivia. Bye-bye. She's gone. We're out of here.
Thanks again.
You're welcome.